So, why am I here? Well, I'm here because I have put together a series of talks on the history of science, and it's intended to supplement what you studied last year in your Theory of Knowledge course. The premise here is that you don't really have a full understanding of the theory of knowledge until you have some understanding of the history of knowledge, and in particular, the history of science. So here's the full title of the entire series of presentations. From the ancient Greeks to Isaac Newton, the history of astronomy, the birth of science, and the origins of calculus. That might sound like an awful lot of ground to cover, and potentially it could cover a lot of material. But I'm going to winnow it down, and I'm just going to try to cover most of what I want to say about ancient Greece in the next 30 minutes. Then we will skip over the next 1,500 years or so because, well, not a whole lot was happening in science. And next time we can quickly get right into the scientific revolution. So today I just want to tell you enough to give you a good idea of the clever ways that the Greeks used careful observations, geometry, and deductive reasoning to answer some very basic questions about their world. But keep in mind, when I say basic, I don't mean easy. These were tricky questions. Now, you might wonder why I include the origins of calculus here. Well, that's because one of the key themes is that the history of mathematics is closely intertwined with the history of science. The two often go hand in hand. And finally, another question might be, why the focus on astronomy? The short answer is that for a long, long time, there wasn't much going on in science except for astronomy. And the reason for that has to do with the fact that science involves recognizing patterns, finding regularities, formulating hypotheses to try to come up with fundamental principles, and then making predictions based on those hypotheses and then testing the predictions. The problem is that events on Earth, at a superficial level at least, seem governed more by chaos than by regularities. Of course, we recognize that one season follows another in a very predictable sequence. But when you start trying to predict the weather, it's hard to do that with any accuracy beyond, let's say, 10 days. And that's now with all the modern technology that we have. So the weather is one good example of the sort of chaos that you run into when you're trying to investigate events on Earth. In contrast, as the Babylonians and the Egyptians discovered early on, before the Greeks, the movements of the sun, the moon, and the stars are exquisitely periodic and therefore highly predictable if you make enough observations. Now, why do I start with the ancient Greeks? Well, the short answer is that ancient Greece is simply a convenient place to start. But let's ask a more fundamental and more interesting question. Why do the ancient Greeks get so much of the credit for founding Western civilization? That is, for making so many foundational or transformative contributions to science and astronomy, philosophy, mathematics, engineering, and the arts. Well, in fact, they do deserve a lot of credit here, but they certainly didn't invent these subjects. As I alluded to earlier, the Babylonians had already made many major advances in astronomy, including the ability to predict lunar and solar eclipses. The Egyptians, meanwhile, had essentially invented the calendar we use today, wherein there were 12 months of 30 days each, plus an extra 5 days every year for 3 years, and then 6 extra days every 4th year to account for what we call the leap year. Well, there are perhaps a number of reasons why the Greeks get so much credit, and here is a clue to one of them. Winston Churchill once said, "History is written by the victors." This is Alexander the Great. He was the son of King Philip of Macedonia, which lay just north of ancient Greece. When Alexander was about your age, King Philip hired the already famous philosopher Aristotle to move up from Athens and be Alexander's tutor. As a result, Alexander developed a great respect and love for Greek intellectual culture. He also developed a passion for war and conquest, and in a relatively short amount of time, he established the largest empire that the world had ever seen. Part of his goal was to spread Greek culture throughout the known world. So he leads his army through Asia Minor down into Egypt, which he quickly conquers. He establishes a new city there, which he names after himself. Alexandria will quickly become the most important center of learning in the ancient world. The Greek conquerors will build the famous Library of Alexandria, and scholars from all over will come to study its collection of ancient texts. Alexander then takes his army east and conquers the Persian Empire. Now, the Persians had conquered the Babylonians, but they allowed the Babylonian priests to preserve their scientific and mathematical learning in their texts. And when Alexander marched into Babylon, he wanted to make all those texts available to Greek scholars. There was just one problem. They were written in cuneiform on clay tablets. So he persuaded the Babylonian priests and the Greek scholars to work together to translate all that accumulated ancient knowledge into Greek. As it happens, Alexander's methods of persuasion were very effective, and that's how Greece was able to benefit from earlier work in astronomy by the Babylonians. Meanwhile, the use of cuneiform soon died out, and the vast majority of those original clay tablets were lost to history. The ancient Egyptian language and the method of Egyptian writing suffered a similar fate. That's why later European historians, either through ignorance or bias, gave so much credit to the Greeks. With that little digression behind us, we begin our discussion of Greek astronomers with a fellow named Anaximander. Now, Anaximander was a student of a guy named Thales of Miletus, and Thales himself was a fairly famous scholar and is still today known as the father of Western science. So Anaximander had a very good teacher, but he struck out on his own and made his own discoveries. And in particular, he developed the notion of celestial spheres. Now, anyone who observed the night sky for a few hours would quickly conclude that stars generally rise in the east and set in the west, just as the sun and the moon do. But if you look to the north at night for several hours, as Anaximander did, you would notice something very different. And thanks to modern time-lapse photography, I can show you fairly quickly what it took Anaximander several hours to realize. To Anaximander, the North Star appeared to represent the top of the axis around which a giant sphere rotated. He conceived of the stars as fixed points of light on a huge, rotating, transparent crystalline sphere. The Earth he thought of as a cylinder floating in an infinite space surrounded by the sphere of stars. Those coming after Anaximander realized that the sun, the moon, and the planets did not travel in synchrony with the stars, so they invented a separate sphere for each of those bodies. We can appreciate Anaximander's originality by comparing his theory with that of his teacher, Thales. Thales thought of the Earth as a short cylinder or disk floating in a giant ocean, and he felt that there was really only one up and one down. For Thales, things fell in one direction only, from his conception of high to his conception of low. In contrast, Anaximander thought that whenever you go in any direction away from Earth, you are effectively going up or higher, and therefore he conceived of the Earth as being at the center of the universe. Karl Popper, a 20th century philosopher of science, calls this idea one of the boldest, most revolutionary, and most portentous ideas in the whole history of human thinking. Moving on, let's ask a question. When did someone first have the idea that the Earth revolved around the Sun and not the other way around? Well, it was in the 3rd century BCE, and this idea came to a fellow named Aristarchus of Samos. It would take almost 2,000 years before his view became widely accepted as the correct one. Here are some of the questions that the ancient Greeks were thinking about. Is the Earth round or flat? How far away is the Sun? How big is the Earth? It turns out that to get to the answers to those questions, a good way to start is to first find the answer to another question. Which is closer to us, the Sun or the Moon, and by how much? This is the question that Aristarchus set out to answer. Think about the phases of the Moon. Aristarchus would agree with us that the Moon revolves around the Earth over a period of 1 month. If we assume, as Aristarchus did, that what we see of the Moon depends on the sunlight that it reflects, we can quickly understand that we see a full moon when the Earth is almost directly between the Moon and the Sun. Similarly, we can deduce that a new moon, that is, the time when the Moon is not visible to us, occurs when the Moon is more or less directly between the Earth and the Sun, and none of the light it reflects can reach us. In fact, when the Moon is precisely between us and the Sun, we get a solar eclipse. So the Moon must be closer to us than the Sun. The more interesting question is, how much closer is the Moon? Well, Aristarchus realized that when we see a half moon, a line connecting the Sun and the Moon and another line connecting the Moon and the Earth must form a right angle. Then he imagined the right triangle shown here. He measured the angle theta by direct observation. He found theta to be about 87 degrees. So he knew the third angle must be 3 degrees because the angles of a triangle all have to add up to 180. Now, trigonometry had not been invented yet, but the Greeks by this time knew enough about right triangles and similar triangles to know that when you know all 3 angles of a triangle, you also know the ratio of one side with any other side. So, given that theta was equal to 87 degrees, Aristarchus determined that the ratio of side S to side M was 19. In other words, the Sun, compared with the Moon, must be 19 times farther away from the Earth. Aristarchus also understood the concept of the angular diameter of an object at a distance, as this diagram illustrates. Even if you don't know the actual distance to the Moon or its actual diameter, you can measure its angular diameter by direct observation. It turns out that the angular diameter of the Moon is about half a degree, which, coincidentally, is also the angular diameter of the Sun. That means that if the Sun is 19 times farther away than the Moon, but has the same angular diameter, it has to be 19 times as big. Aristarchus also figured out that the Earth was roughly 3 times bigger than the Moon based on observations during a lunar eclipse, and once again the application of geometry and deductive reasoning led him to his conclusion. As it turns out, this was a very good approximation. So, he estimated that the Sun is 6 times the size of the Earth, more or less. Now, the conclusion that the Sun is very large, larger than the Earth, and very far away, has an important consequence if you are interested in knowing whether the Earth is round or flat. It means that the Sun's rays hitting the Earth are essentially all parallel with each other. Now, if you wanted to challenge me on that statement, you would be justified based on this diagram. Because look, you could draw these 2 rays emanating from opposite sides of the Sun and converging at the same point on Earth, and clearly these rays are not parallel. But this diagram is not drawn to scale. Because of Aristarchus's previous finding, we know that the angular difference between any 2 rays can never be more than ½ a degree. And this effect is negligible for the experiment that our next Greek astronomer is going to do. Imagine that the Earth is flat and you have 3 cypress trees of the exact same height at these 3 locations. Now you and your 2 assistants measure their shadows on the same day at the same time, let's say at noon. Because the sun rays are all parallel, the lengths of their shadows should all be the same. But if the Earth is round, then the shadows should get longer the farther north you are. Along comes Eratosthenes, mathematician, geographer, astronomer, and chief librarian at the Library of Alexandria. We are still in the 3rd century BCE, shortly after the time of Aristarchus. Eratosthenes is very interested in shadows. Here's a map of Egypt. Eratosthenes is up here in Alexandria, along the north coast of Egypt. He hears the story of a well down in Syene, a small town on the southern frontier of Egypt. As it happens, Syene is very near the latitudinal line that we now call the Tropic of Cancer. We will come back to that in a moment. So here is the well. Most of the year at noon, the sun is more or less to the south, and the well is almost completely in shadow. However, at the summer solstice, the first day of our summer and the longest day of the year, the sun at noon is directly overhead in Syene. And the well is completely filled with sunlight. So what's going on from our modern viewpoint? Here is a modern map of the world, and here is the Tropic of Cancer, the dotted red line. And here is the orbit of the Earth around the sun. The Earth's axis is tilted so that on the day of the summer solstice, the northern hemisphere is maximally tilted toward the sun, so that if you are standing somewhere on the Tropic of Cancer, the sun at noon is directly overhead, and you will have no shadow. But if you are standing north of the Tropic of Cancer, like this fellow here, you will still have a shadow at noon because the sun is a little bit to your south. Now, Eratosthenes does not know about the orbit of the Earth around the sun or the tilt of its axis, but he does know that when he plants a pole in the Earth at Alexandria, it casts a shadow at noon on the day of the summer solstice, pointing north. He has just proven that the Earth is round, but he intends to go further than that. But the next question is, how does he know exactly when it's noon? Well, he measures the shadow at different times of the day. In the early morning, the shadow is long and pointed mostly towards the west. As the morning progresses, the shadow gets shorter and shorter, and at noon, it points due north and is at its shortest. And then the shadow starts getting longer as the day progresses further. Well, all he has to do is mark the spot of the shadow over this course of time, and he knows that the shortest shadow is the noon shadow, and that's the one that he's interested in most. So he measures it. He now knows the height of the pole and the length of the noon shadow. So now he knows the length of two sides of this right triangle, S and L. If he chooses to, he could use the Pythagorean theorem to find the length of the third side, the hypotenuse. But most importantly, he can simply use the ratio of S to L to find the angle theta. He finds that theta is 7 degrees, which is about 1/50th of 360 degrees. In other words, 1/50th of a full circle. He hires a guy to measure the distance between Syene and Alexandria. It is about 5,000 stadia, or about 800 kilometers. Syene is almost directly south of Alexandria. Taking into account the parallel nature of the sun's rays, the angle theta, and the theorem recently proven by Euclid that alternate interior angles formed by a line intersecting two parallel lines are equal, he determines that the angle at the center of the Earth between a line to Alexandria and a line to Syene must also be 7 degrees. The rest is simple math. If 1/50th of a circle equals 5,000 stadia at the surface of the Earth, then the full circumference must be 50 times that length, or 250,000 stadia. This was, in fact, a very accurate estimate. If you want to be nitpicky and you think it through, you might realize that the estimate should be even more accurate if Syene were, in fact, directly south of Alexandria. Still, Eratosthenes' accomplishment is pretty impressive. We will pick up the story next time with some final words about Greek astronomers, and then we will fast forward quickly to the beginning of the scientific revolution.